Oh, mute button. Thank you. This is why I appreciate all the feedback in the chat. Yeah. Woohoo. Yes. Welcome everyone to another podcast broadcast of This Week in Science. It's just me, Dr. Kiki, and Blair is out tonight. She has some other work responsibilities, so she's not able to make it. I am feeling a little under the weather, so I'm going to do the best I can here to be excited and happy, but I'm a little like wah. So we're just gonna get going here. Gonna make This Week in Solo Science. Yes, Identity 4. I'm so glad you're here. Thanks for being here. Everybody, remember that this stuff gets cut out for the podcast. And if I have any issues during the show, hopefully Rachel will edit them out and turn them into the podcast, or not the stuff I have problems with becoming the podcast, all the good stuff to be the podcast. That's what I hope for. And additionally, like, share, get in the algorithms, that whole business. Let's get moving. Let's start this show. Yeah, let me get to the right place. Where is that inbox? Where's that place I wanted to see? Yes, here it is. My run sheet so that I can start everything in 3, 2. This is TWIS. This Week in Science, episode number 1051, recorded on Wednesday, March 11th, 2026. Gnaw on this for a bit. Hey everyone, I'm Dr. Kiki, and tonight we will fill your head with freedom, origami, and chewing. But first, disclaimer. With everything going on right now, it's a privilege to take time for curiosity and wonder, to talk about science and discovery with friends like you here on This Week in Science. Coming up next.
I've got the kind of mind that can't get enough. I want to learn everything. I want to fill it all up with new discoveries that happen every day of the week. There's only one place to go to find the knowledge I seek. I want to know what's happening, what's happening, what's happening this week in science. What's happening, what's happening, what's happening this week in science.
Good science to you, everyone out there. Thank you for joining me for another episode of This Week in Science. I'm so happy to be here to talk about everything that's going on. Well, not everything. All the stuff I think is interesting from this last week that I want to talk about with you. I've brought you my favorite stories of things that I dug through over the last week and decided were worth it. I've got stories about, science generally in the world. I've got some tamper-free viruses, new vaccines that utilize origami, maybe? I don't know. Garbled messages from space, some human-centered computing, and gnawing. A gnawing need to chew. I have a gnawing need to chew. Do you? Do you? Anyway, welcome everyone. I hope that you are here to enjoy the evening or whatever time, place, space you are in right now. It was time change week for a lot of places in the United States this week, and what I thought it was very interesting to see how it impacted my son's high school at drop-off in the mornings. And I don't know how you all feel this week, and if it's getting any better day by day, this time change, this hour difference. But the last 2 days after the school is supposed to have started already has gotten longer and longer. And yes, we were one of those later families dropping off this morning, because the time change just doesn't work with the teenage brain, just like it doesn't work with any pet that you feed at a certain hour. 2 states, I think, have adopted or are looking at adopting standard time year-round, and we are seeing more advancement in the movement by various places to make daylight savings time normal wherever we are. So we might see a patchwork across the United States, depending what different states want. Yeah, right now, Arizona, Hawaii do their own thing, but it'll be very interesting to see the natural experiment that occurs by different states choosing their approach to time and space and place. And oh my gosh, it's just going to get harder and harder to be able to schedule any meetings if you're working with people in different time zones. It'll be fun though. All right, time for us to jump into the science. I want to remind you that subscribing to TWIS as a podcast is really easy. You just find us on your favorite podcast platform. We're on YouTube, Facebook, and Twitch, broadcasting live every Wednesday evening, 8 p.m. Pacific time, and our videos are stored those places as well. I think Twitch, it's only like for 2 weeks unless people make clips and post those, but that's up to you if you're on Twitch and want to do that. Every time a show is published, if you are subscribed to us, you'll get a notification and you'll know there's something new. Otherwise, just search for This Week in Science wherever you want to find your science news. TWIS.org is our website. And now it's time for the science. La, 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 la. I don't have like Blair or Justin to say to prompt me this evening, so I'm just having to dive in as I go. My first story tonight, my first two stories tonight are a little critical of how things are moving in the science space in the United States. And you know that every year we love to report on the Ig Nobel Prize winners because it's such a wonderful, just jovial, just joyful way of looking at science to talk about the tongue-in-cheek way that the Ig Nobels look at studies that maybe were approached with all seriousness, but can be interpreted as not necessarily. And maybe sometimes science can be done for fun. Oh my gosh, have we ever thought about that? But anyway, we love the Ig Nobels. And this week it was reported that the Ig Nobels are no longer, the award ceremony at least, is no longer going to be held in Massachusetts in the United States. It is going to move to Europe. Next year, this year, the Ig Nobels are going to be in Switzerland. They are going to be in Zurich on September 3rd. And from now on, they will be held in alternating years in different European countries, always coming back to Zurich because they have a lot of individuals who are international award winners. And the people who run the Ig Nobels, Mark Abrams, the Ig Nobel founder, made a statement on Monday this week saying that during the past year, it has become unsafe for our guests to visit the country. We cannot in good conscience ask the new winners or the international journalists who cover the event to travel to the US this year. I find it very interesting that they have made a decision that it'll be it's a general plan, but that this is for good, that until and will things change in the US to make it easier for people to travel here, for scientists and journalists to come and not fear for their lives or their safety? I have no idea. So this is something that's making me sad this week. And it just falls on with so much that we hear now about researchers and knowledge and experience leaving the United States for opportunities that are better now and less monitored, I think. Anyway, along those lines, I'm hearing you there in the chat. Yeah, it is sad. And Paul Disney, it's a kick in the teeth. It kind of is. Yeah, it's upsetting. Because the Ig Nobels are just wonderful, and it was so great that it was here. We could bring an international community of science together for fun and appreciation of the sillier side of science. And I don't know. I don't know. I don't think of Zurich as silly. I don't know about you, but I don't know. If you live in Zurich, please let me know if I'm wrong. Is Zurich a place that could really enjoy the joviality of the Ig Nobels? Let me know. Along these lines, though, as well, I was going to get to the next story. There is a report in Ars Technica from John Timmer, who has reported on the word spreading that the NIH, National Institutes of Health, is going to launch a series of lectures. They're calling them the Scientific Freedom Lectures. The first one is scheduled for March 20th. The first Scientific Freedom Lecture you would expect maybe to be a lecture from a well-known scientist. It's not. It is a lecture from a journalist who is on the fringes of things. Matthew Ridley, he is a British citizen and science journalist. He's written many books on biology, but he has many fringe ideas about climate change. He follows the idea that the COVID-19 virus was created in a lab, and he has been listed in a UK-based think tank that it has been labeled a climate change denial lobby group. So why is this individual being given the opportunity to launch what is supposedly going to be a lauded series of lectures celebrating scientific freedom? It's a question we can't really answer. This is a project that Jay Bhattacharya, the head of the NIH, wants to move forward. He believes that scientific freedom is important because he has been challenged and kind of gotten in trouble through the years. I don't know. He's the director of the NIH right now, so whatever. But he was one of the signatories of the Great Barrington Declaration that argued that we should only try to protect elderly and vulnerable people and just let COVID spread, without vaccination at all. So he has been historically a good scientist, but there are things that he is on the fringe of. And it's not bad to be a fringe scientist. It's not bad to have an idea that is on the fringe, because very often fringe ideas find evidence that bring them to the mainstream. But it's when we allow the fringe ideas to be the mainstream that we have a problem. Science is not about popularity. Science is not about what you believe. Science is about how the evidence supports a certain hypothesis. And so my question is, why? What is happening? And are they going to have better, or who? Why? What is going on with this? I don't know. I don't know. So anyway, these are my what the heck stories from to start off the show. We should have scientific freedom. We should be able to experiment on things as long as they're not injuring people, as long as you're not harming people on purpose, or for scientific freedom, not giving people treatments that would otherwise help them. There is so much in terms of scientific ethics that need to be upheld. And I don't know. I love fringe science. We talk about fringe science all the time on the show. I love it. I think it's great to talk about it, but we can't let it take over our understanding that it is not the mainstream. These are ideas and hypotheses that have yet to gather the evidence to really have support, but they're there. And it's okay that they're there. We should all have ideas, be curious, come up with stuff. Yeah. I like science as a verb too. Let's science it. Moving on from there, I want to talk about, I'm going to move on since I mentioned the Great Barrington Declaration and COVID. I want to talk about a recent study out of UC San Diego that I find really interesting. So this study ultimately did a phylogenetic analysis of lots of viruses that have caused disease in humans. They looked at the evolutionary markers of mutation and change in these different viruses to kind of figure out, where these viruses are coming from and how they were adapted before they gained access to humans. And the idea, and it says in this UC San Diego press release, that the prevailing model of zoonotic emergence assumes that viruses first acquire adaptive mutations before they can sustain human-to-human spread. So there are very specific mutations that allow them to specifically get into humans, right? But that's not what this study found. It found that a lot of these viruses simply were able, they had adaptations, of course, that allowed them to broadly infect a number of human-related species, so lots of wild species. There was no pre-adaptation for humans specifically, and the changes in the viruses actually occurred most often after they got into people. So it was the sustained transmission in people that was the thing that gave the viruses their power in people to spread widely and cause outbreaks. But really, it wasn't that they were pre-adapted. There was the luck of the draw from one mammalian species to a human, another mammalian species. And then that human maybe had the the immune system, the whole metabolism, everything to allow that virus to grow and to flourish. A lot of people who are patient zeros are the only patient, right? There are a lot of people who get sick from a zoonotic transmission. They end up in a hospital or they don't, but we never hear about it. It is the eventual change that there's one lucky accident where the human is the human is the petri dish that spreads it, and the next human and the next human, and things avalanche from there, right? Or they snowball from there. And so that is what they saw in this study, which I found really interesting. So they looked at controls as well. They validated their approach with artificially selected viruses, not just wild viruses. So they used viruses that were lab created and viruses that were in humans. They looked at all sorts of viruses, and what they found is that there are actually very specific markers in the viruses that are lab fostered versus human fostered. So because of the natural adaptation and mutation that occurs between zoonotic to human and then human to human to human to human, and the way that transfer works, that has one kind of a signature. But if it is a laboratory based organism, a virus, I won't say organism, a virus, that has a completely different signature. And so they went and they looked at the COVID-19 virus, the one that was original. They found one particular virus that they looked at flu viruses particularly, and a lot of those flu viruses had limited genetic divergence from the 1950s, and there was this 1977 H1N1 strain that came from a lab, it had this very specific signature of how it had evolved, and it kept that signature even after it emerged and caused an outbreak in people. But in COVID-19, their results do not see that kind of a signature. They do not see a signature of laboratory cell culture and generational growth, which is not as chaotic or randomized as would be the emergence in a human and human to human to human for an outbreak. Yeah. So anyway, I don't know if they fully set out to test whether or not COVID-19 was or is lab based, but where it comes from and how it set out, how it resulted is that they are able to show the dynamics in a very repeatable way of natural selection and how natural selection works on outbreak causing viruses that precede those human outbreaks, that could allow us to know the difference between wild and laboratory viruses moving forward in the future. But the researcher who worked on this study, he says this work has direct relevance to the ongoing controversy around COVID-19 origins. We find no evidence that SARS-CoV-2 was shaped by selection in a laboratory or prolonged evolution in an intermediate host prior to its emergence. It represents a natural zoonotic event So say what you will. I don't know. It's just science. It's just science. People working, trying, and this study is out. It has been peer reviewed. And of course, now um, it can be discussed. We can talk about whether or not the methods were right. The community can discuss what this research means. So we can talk about how their methods worked. We can discuss these things, and that is what we should be doing instead of allowing political conversations to determine our understanding of an event. Yeah, so tuna bomber 11 or 111, you're saying, so there's markers we can observe that indicate and differentiate lab versus zoonotic origin. And that's exactly right. And so because of the way that the timing of laboratory passage works versus a natural host, or whether there's an intermediate host involved between, say, a bat or a pangolin to humans, like however it works, there are natural natural selection processes that impact the mutations and the genetic change that we see. And so their work comparing viruses and the phylogenies, like all the genetic information and how they may have evolved, they were able to determine that you can tell the difference. You can do comparisons and you can tell a difference. And it wasn't a Chinese study. This is from UC San Diego. So it's it's California. I don't know if some people, what some people think about this, but honestly, I don't think this should be a political issue. And that's one of the things that has become so bothersome to me, right? It's like health. It's how can we stay healthy, right? I want people to stay healthy. I hope you want people to stay healthy too. We can do that by talking to each other and listening to the evidence and also talking about our lived experience. We need to do that. Okay, so now we know that there is a way to potentially determine origin of viruses, but how about fighting viruses? We can talk about how about the vaccines that we use? Oh my gosh. So researchers in this study, they were interested, Harvard University researchers, they have been working on a new kind of vaccine, and it wasn't supposed to be a vaccine for lots of like vaccinating people against diseases. It was supposed to be for cancer. This is something they were developing, a platform they were developing to fight cancer in the human body, which is multifaceted, and it depends a lot on the cellular environment, the tissue environment, and so many factors. We have been able to show, though, that the vaccine approach can be effective to cancer. So anyway, they have been working on a platform at the Weiss Institute, Harvard University, Dana-Farber Cancer Center. They have developed what they call DNA origami nanotechnology. It's called DoryVac, and this isn't Dory like the fish. It's DNA origami vaccine, right? So, but during the COVID pandemic, they saw the mRNA vaccines doing well, and they're like, "Oh, that's interesting." But they also saw some of the issues with the mRNA vaccines that were being used, which in the instance of SARS-CoV-2 and its rapid evolution as it moves through populations into different strains, we have to keep getting updated vaccines to be able to stay updated in our ability to fight it. They have been able to, with their DoryVac vaccines, they wondered if they could create a vaccine that also harnesses an adjuvant, which is so it's like the antigen is presented, which is the part that your body reacts to and goes, bad, it's foreign, get away, right? Your body goes tribal and like attacks. And then the adjuvant is the other part of this, which is special. The adjuvant is a part that accentuates the body's response to the vaccine or to the antigen. So anyway, the DoryVac people, they're like, hey, I wonder if we can do better than mRNA vaccines, which are also being looked at to treat cancer, but they have some issues. Like people don't all react the same to them. They're not 100% effective all the time. There are a lot of factors that are unpredictable. And so they think with their Dorivac system that they might do better. So they targeted a peptide region, the HR2, which is conserved in the spike proteins of SARS-CoV-2, HIV, Ebola, and other vaccines. And so they're thinking maybe we can get these HR2 peptide regions and really make a big response that the body is specifically going to attack anything that seems spiky with relation to this. So they used their vaccine on mice, and they also did a preclinical trial on human lymph node tissue that they had an organ on a chip technology so that basically a lymph node in a dish, not a synthesized lymph node, because it's like this whole system of microfluidic fluid flow and everything. Anyway, they compared the SARS-CoV-2 mRNA vaccines against their Dorivac vaccine, and they showed that in the mice, the Dorivac vaccine had a similarly strong had a really strong, potent effect in the mice, but it also had a similar effect in the human lymph node in this organ on a chip technology. The big thing about the Dorivac is not just that, okay, we've got a new design for creating a vaccine, woohoo. mRNA actually needs to be kept very carefully. It has to be cold, there needs to be liquid, all this stuff. And these vaccine components apparently are cheaper and easier, more to get places without degradation. So the idea is that if they work in humans, they could potentially create a very flexible platform, what they call it, a chassis, with a lot of advantages to be able to add an adjuvant and the antigen to their origami design to actually fight various vaccines. But in this case, they were able to have precision delivery to immune cells, and they did well. So we'll see whether or not this is something that moves forward. So far, they're at a point where they are showing its effectiveness and lack of uh, mortality, right? So keeping mice alive, not damaging these lymph cells, having the effect that they want. And they're hopefully will move on to human studies very soon. So they do think that they have a promising safety profile, but we'll see where that goes. We'll see. If we have easier ways to get vaccines, get treatments to people, this would be just so amazing. Yeah, go Google adjuvant. Why don't you? Why don't mRNA vaccines break down in the warm human body? So it's not the problem that they break down in the warm human body. It's once they get into the human body that they're where they need to go. So that's not the problem. So they get into the human body and they're there, and they're held in a liposome, usually based on another non-body threatening virus, so adenoviruses or others that are used commonly to present stuff to the body. But they end up in the human body and they're where they need to be, and so that is not the issue. It's more, can they last long enough on a shelf, on a plane, in a backpack? How do they need to be treated? Or I don't know, how resilient are they? And so apparently the mRNA vaccines are not super resilient, and so we're not going to be able to get a lot of the newer vaccines of this type of the mRNA technology to places that are remote, or if you have an issue where power's gone out because of a hurricane, it could cause issues with the mRNA vaccines being able to stay working, to be able to keep working. So anyway, this new vaccine type, we'll see how it works. They seem to also be having amazing ability with in how it works in cancer. It's been very successful in cancer. And so in the image that I've kept up on the screen here, and also I'll tell you for people who are listening to the audio, there's something of a little, like, it looks like a Lego, and it's two-sided, and it's square block-shaped nanostructures. One side has the adjuvant, and the other side has the antigens. So they're opposite each other. But because of the way it's structured, apparently because the antigen attracts the immune cells, and then the adjuvant is there to go, "Ha ha, I'm here, now do more." Um, the way that they face off and the spacing between the two sides because of the structure of the vaccines, um, it makes them very effective. So the origami aspect is that the square block shape, they are self-folding. So these structures actually fold into this shape that they present. And I think that's just the nanotechnology field and the way that we are using molecular forces to create structures, I think is just, it's amazing. This kind of work is so cool. So anyway, we'll see. Yeah. So storage and delivery, it could be, so mRNA sensitive to heat and drying out. Others are sensitive to cold. Like everything has its own factors that make it, all of our pills or shots, like all the stuff we use um, to keep, that we send from place to place. They each have their own profile for what the set of conditions in which they will continue to work. And so everything, sometimes you get a blister pack, sometimes it's just a bag or a box or whatever. But it's, yeah, this thing apparently, once you make them, they work very well and are more stable. So I think that's very, very fascinating. But okay, let's move away from this stuff and into some different technical issues. Like, what if I were transmitting this whole conversation to space? What if I were trying to talk to aliens? If I were the opposite of SETI, if I were actually transmitting this? Would it be a tight beam to another planet? How would this signal go out, right? Apparently, some researchers associated with SETI have published in Astrophysical Journal this week their new idea of why we have not yet heard the signals of alien intelligence coming from space. And their analysis in the Astrophysical Journal was actually to look at our own solar system and the effects of solar winds, solar storms, various space weather outbursts on the communications of spacecraft within our own solar system. So it's kind of interesting that they were looking at this, and what they found is that, hey, solar wind, it takes more tight beam, narrow range transmissions and broadens those transmissions over, many hertz. And so, woo, the transmissions get broadened. And while we're sitting here looking for narrow band transmissions, perhaps we're missing them because they're broader. So anyway, that's all they're saying. And I think it's very interesting, to come up with the creative reasons. This is again going back to that fringe science, right? You got to come up with explanations. Why, if we assume that there is intelligent life in space and that it's been transmitting as long as we have, or whatever is within the range, why have we not sensed it? Why haven't we gotten that signal? We've gotten lots of signals, so many signals from space, and none of them have been intelligent in nature. The researchers say that this new analysis, this new understanding highlights what they say is an overlooked complication. And so even if there's a really narrow signal when it leaves home, maybe it's been broadened and stretched and turned into something that is less detectable by other stars, solar systems, and all sorts of weather that the signal passes through on its way to us. Yes, Kevin Reardon, we absolutely should have listened closer to Oumuamua. Maybe it was a subspace relay. Yeah. Anyway, I have no idea what if we'll be able to figure out a new way to look at the data, look at the signals that we are measuring to be able to see whether or not there is something there we have missed, or find a new way to look at things moving forward. But it's interesting. Do you think we're alone? I don't know that. I don't know, right? It's so weird. We only have one planet right now, and going to Mars or the moon or other places, it's still that is a technological challenge, right? There's a whole bunch of engineering that has to go into place, and we're still, while that's happening over how long a time period, we're still only living here on Earth. This is our basket. This is it. All the eggs are in it. Ah, yeah, Kevin Reardon, you're not alone. I'm not alone either. I have all of you. Thank you. John Hogan is saying entangled particles might be the way to find communication from aliens, and maybe that's another thing. But until we have the way to decrypt an alien quantum communication, I think we're working on it ourselves now, but I think it's going to be a very interesting, that's an interesting task. Lon Koenig, you're saying everyone assumes that alien life operates on a time scale similar to ours. Other biologies might be drastically slower or faster than ours along with their signals. I absolutely agree. I love the idea that there is intelligent life that's much older and bigger and slower than we are, and that the intelligence and their communications is somehow just we're not catching it because we move we're like the ants moving underneath them, right? We're like trees or ants from Tolkien, right? Move so much more slowly until they have to speed up to do something in the universe that it was taking place in, but otherwise there's no need. And they communicate in a different way. And how does that happen? I think our understanding of how different species on our planet communicate in multiple different ways is important for that. And I think it will be essential for us to understand beyond the vocal transmission of animals. I think we're going to have to figure out how to bring in the local body language factors, right? So how much information can be conveyed in the slight movement of feathers around a bird's eye or on its body that we are not interpreting as carrying important data. Oh, that's funny. Look, they just do a special dance during mating, right? Maybe there's got to be so much more there. And the assumption that all intelligent life will communicate as we do. Very anthropocentric. Standard for humans. But anyway, and speaking of humans, I saw Patrick commenting on this before the show got started and at the beginning of the show. The company that we've talked about previously, who has been developing human brain cell computers and computation. They've been having their computers play video games for the last several years. Previously reported they played Doom. That's great. Corical Labs. They announced a while ago that they were working on creating basically hard disks, right? Or I guess this would be biodisks, soft disks or servers that could do compute, right? Could have computing power for various purposes. And so they've been developing these components and these servers that can be used. And they're doing things. It's great. The neurons are able to act as computers. They can play video games. That's amazing. But okay, now the big news is that they're going to open 2 biological data centers, one in Melbourne and one in Singapore. They're working with a different company. And also they're doing a validation phase initially at Yonglou Lin School of Medicine at National University of Singapore. This is going to eventually be the Singapore project will have as many as 1,000 units if they are able to scale there. And I think what they have to do is grow the server system, right? The networking to see if they can actually scale larger and larger. So they have these biological computers that are lab grown neurons that combine with a silicon chip. And so software and BioWare can actually compute. You can get software running on the BioWare. That's haha funny software. That's kind of funny. Um, but I'm wondering how flexible, how dynamic, like I think there are going to be differences between the servers that we currently consider as our data servers versus the computing of a bio server. And so I think these pilot programs, they're initially going to be figuring out the extent to which different computing processes can take place on them, right? So the current setup for this Cortical Labs 1, CL1, has about 200,000 neurons per unit. And this is not as much as some of the earlier reporting actually said that they were going to be using or that they were trying to use. So they've ended up at this amount of neurons. I don't know why, but this is how it's working. I think it's just going to be fascinating to see how it moves forward. It's not a conventional silicon processor. Yes, I think Lon said it. Somebody said wetware, right? Nope, tuna bomber. Yeah, it is programmable wetware, which it learns and self-organizes in that that's not the kind of thing that normal silicon chips can do, right? So we have silicon chips with set circuits, right? This is going to be biological material, neurons that are capable of developing synapses with each other, of developing their own relationships and creating internal networks plastically. We'll see. And after my interview a couple of weeks ago with the astrocyte researcher and learning how important astrocytes are to the plasticity of synapses, I'm now actually really interested if they're going to have to incorporate astrocytes, or if how they're going to be limited if they're only using neurons, because it seems like there's a lot more complexity to our brains that is not going to be paralleled in this synthesized system. But anyway, I think this is a fascinating piece of news. The idea that these brain computers can do a lot of work, I think is fascinating. And yeah, one of the points that they bring up, which I think is interesting, is that they are lower powered. They don't need as much resources for power as modern data centers. So because of the neuronal electrical needs, they don't need as much energy. However, they are going to need food. They're gonna be fed. They have to be fed. That's gonna be a lot of serum. A lot of serum to keep those brain cells happy and to ensure that they are maintained. So that's a lot of water still, and a lot of resources to develop the serums that make the computers happy. So there are other issues that we should be considering. If anyone has worked in lab cell culture, you know what it takes to keep cell cultures clean and happy. And will they be able to do it? Can we do it on a large server farm scale? I think this is going to be a very interesting experiment. I'm very interested to see how this goes. Yeah. Anyway, it won't be your normal artificial intelligence, that's for sure. All right, I have one more story for the night, and I want to talk about chewing. As you chew on all the information that I gave you. Yeah, your brain chews on this, right? You know, turn it over in your brains, let your neurons kind of go on the information. University of Michigan researchers decided to study rodent chewing habits. And why would they study rodent chewing habits? Well, it's not just because we chew everything has to chew unless you're slurping out of a straw or a proboscis. But in this particular case, the researchers have had to have decided that it would be important to see what is happening during chewing and if neural circuits are only related to the mechanical aspects or if there's other stuff going on there. So the old view is that, according to Baudouin, associate professor at the University of Michigan College of Literature, Science, and the Arts, is that everyone thought that it was just, hey, motor messages, drive the chew behavior, chomp, chomp, chomp. It's just messages from the brain, like you get food in your mouth, that goes back to the brain, and the brain goes, huh, chew. Or you think to yourself, oh, I'm going to chew. But they've also been looking at things like grinding of teeth or bruxism, oral issues, malocclusion that occurs. But a lot of habits happen in people's lives that we can't control, that it's not just mechanical. You don't have anything in your mouth and you're still chewing, you're grinding. Ugh, it's no fun. So they just published their study in the journal Neuron about how they looked at the neural pathways in rodents. They didn't look at people brains, but they looked at rodent brains. They looked at a lot of rodents, in fact, because rodents have to chew very often. Squirrels, for instance, if they don't keep chewing, their teeth are going to grow. There are a lot of rodents, those front teeth, they just keep growing and growing and growing. And if you don't keep chewing and basically sawing off, sandpapering the teeth, then that can cause huge problems for the rodents. And so they were looking at the issues of sensation in the mouth and the connection of those sensations to the brain, and they identified a new neural pathway that connects not just the mouth to the motor cortex for the mechanistic aspects, but connects it to your dopamine release centers. So related to the actual reward system. So the reward part of the brain is triggered when you chew. So the sensation of stuff in your mouth, your teeth, and all the stuff around it in your mouth, they sense that, and that sensation goes to the brain, and the brain goes, "Oh yeah, chew more. Yeah, yeah, chew. That's great. Oh, you got food in your mouth? That's sensey. Ooh, chew more." And so the dopamine is like, "Yeah, do that. Keep chewing. Keep chewing, whatever. Keep chewing." Um, and they are saying that by understanding that there is a dopamine controlled pathway to chewing, that this explains or could potentially lead to treatment for people who grind their teeth, who have issues of bruxism and other chewing issues that we haven't been able to think about before. They showed in their study that disrupting the pathway stopped the rodents from gnawing. They had problems. Their teeth grew too long. And so when they turned it back on again in the nucleus accumbens in the reward pathway, then cute little squirrel started chewing more and his teeth were able to be ground down and more manageable. Anyway, I think it's just fascinating. There are new things being learned all the time about things like chewing. We didn't realize that there was a control, that it's not just a reflex to chew, that it's controlled in a reward pathway basis. It's motivated behavior. This is, of course, all controlled top down too, because you can decide to chew or not to chew, but that there is a sensory system motivation to chew, I think is really fascinating. Anyway, we know about rodents chewing now. There's trigeminal neurons that are involved in making sure that we're able to gnaw. And of course, we haven't looked at it in people yet, but maybe it can explain a lot in humans as well. But also maybe not. Sorry, not sorry. I'm not sorry. And this could also, so Armandot 3111, you're saying, I feel like the same is true of swallowing. So you can swallow or not swallow. And there also may be not just reflex-based mechanical muscle reflexes happening, but perhaps there are sensory aspects as well. I mean, there's a choke reflex, there's all sorts of things that are involved that are reflexive, but perhaps there are much larger, maybe there's a larger network of neural pathways that we were not aware of before that control very basic behaviors that we take for granted. And yes, to chew or not to chew, that is the question. All right, everybody. Tuna Bomber 111. Biology is fascinating. Life is fascinating. The world is fascinating. And I appreciate this opportunity to have hung out with you and talk about the stories that I thought were fun this week, that were interesting, that were thought-provoking. There are, of course, many, many more stories out there that are worth talking about and discussing. And I hope you find your own. I'll continue to keep looking until next week. And we are going to stay curious, right? Anyway, it is my time. And it is, wow, under an hour. Here we go, everybody. This could be a first. What? I want to say thank you so much for joining me tonight. It really has been a joy to talk with you about this. It is my privilege. And so thank you for being here. I really am glad you're here. Thanks for listening. I hope you enjoyed the show. Shout outs to everyone in the chat room. Thanks for chatting. Thanks for thinking. Thanks for being here with me. Fada, thank you for your help with social media. I hope I've gotten it fixed now for you. And for the show notes work that you do. It is essential. Gord, Aaron, Lore, others, thank you for manning the chat rooms and making sure they're safe. But this is really something that everybody does. Thank you so much for making sure we are all in a place where we respect each other's opinions and can have fun. Identity 4, thank you for recording the show. Rachel, thank you for editing. And thank you, of course, to our Patreon sponsors. Thank you to Aaron Anathema, Adam Mishkan, Alan Viola, Ali Kaufman, Andrew Swanson, Artem, Arthur Kepler, Bob Calder, Bob Coles, Brendan Brian Carrington, Chris Wozniak, Christopher Dreyer, Christopher Rappin, Craig Landon, Craig Potts, Daryl Myshak, Dave Wilkinson, David E. Youngblood, Don Mundus, E.O., Eden Mundell, Eric Knapp, Flying Out, Fredis 104, G. Burton Lattimore, George Corris, Greg Briggs, Jack, Jason Olds, John Atwood, John McKee, John Ratnaswamy, Johnny Gridley, Ken Hayes, Kent Northcote, Kevin Parachan, Kevin Reardon, Kurt Larson, Lon Makes, Lauren Gifford, Marjorie Gertz, Marjorie or Mary Gertz, Marjorie, Mark Hessenflow, Mark Jenkins, Noodles, Patrick Pecoraro, Paul Disney, Paul Ronovich, Philip Shane, Pierre Velazar, Richard Badge, Robert Lorlin, Robert Farley, Rodney Lewis, Rudy Garcia, Remy Day, Sean Lewin, Clarence Lamb, Shubrew, Stephen Albaron, Steve Leisman, aka Zima, Tony Steele. Oh, wait, I missed a couple. Sue Doster, Teresa Smith, Tony Steele, and Vegard Schefstad. Thank you all for your support on Patreon. And if you would like me to read your name at the end of the show, please head over to Patreon and support the show at $10 a month or more. I will read your name at the end of the show. But really, any Patreon support is helpful. If you are able to support TWIS in an ongoing fashion, it is very valuable for us for keeping this show going and making sure we're able to stay bringing you this news on a weekly basis as much as we can. We will be back next week. And on next week's show, we'll be back Wednesday at 8 p.m. Pacific time, broadcasting on our YouTube, Twitch, and Facebook channels live. Blair's going to be gone again, so I'll see what I can do about getting somebody else to talk to, but I'll be here. And if you want to listen to us as a podcast, search for This Week in Science wherever podcasts are found. If you enjoyed the show, make sure your friends subscribe too. You want to have something in common to talk about, right? For more information on anything that you've heard here today, show notes, links to stories, that's going to be available on our website, twis.org. You can also sign up for our newsletter. I'm going to send one someday, I promise. And I will not sell your email. I will not do that. I'm not that person, okay? We love your feedback. If there's a topic you would like us to cover or address or a suggestion for an interview, please let us know on one of our social media accounts or send us an email. And if you're going to send us an email, put TWIS in the subject line so the email doesn't get spam filtered into one of those space-based garbled messages that SETI can't can't find. Yeah, don't do that. Anyway, oh my, look at me going here. We look forward to discussing science with you again next week. And if you have learned anything from the show, please remember, it's all in your head.
This week in science. This week in science. This week in science. This week in science, it's the end of the world. So I'm setting up shop, got my banner unfurled. It says the scientist is in, I'm gonna sell my advice. Show them how to stop the robots with a simple device. I'll reverse global warming with a wave of my hand. And all it'll cost you is a couple of grand. 'Cause this week's science is coming your way. So everybody listen to what I say. I use the scientific method for all that it's worth. And I'll broadcast my opinion all over the earth. 'Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. This Week in Science. Science. I've got one.
Woo! Oopsies. We have reached the after show. Thank you, everyone, for joining me this evening. I love that you wanted to spend the evening learning about science, talking about science, hearing things. Yeah, let's all hope that we're not just a brain in a vat. TM. That's what I hope. I don't want to be your computer, anyone. I am me. You are you. You go have your own fun. Yes, I'm not a brain in a vat. TM. Okay, that's enough. I should go to bed. Oh yeah, there is an Alice. I think it's Sweden, Patrick Pecoraro. There's red lights that they're using now. It's interesting. We'll see how that works. I also wonder how it will impact driving and navigation and night vision. Red light is often better for everyone in terms of not vision at night, but it's gonna be very. I think it's very interesting. Yeah. Oh, Paul, yes, writing a presentation about the sun. Well, that's awesome. That's great. Oh, could be a Boltzmann brain. Well, fine. There's that too. One if by. Yeah. Anyway, I am a little bit under the weather this evening, and so I'm not gonna stay late. Yeah. Unfortunately, I'm not gonna stay late and hang out. I would like to, but I probably should get my rest so that I feel better tomorrow. I'm running the annual Science Talk conference, virtual conference right now. And so I gotta keep going, right? We gotta keep going and doing. Are you in my imagination? I hope not. I hope you're not all AI bots in my chat. I think that would be really sad. I mean, that would mean AI was very advanced years ago, so I won't go there. Ooh. Oh, fantastic, Paul. That sounds great. What we used to think it was made of. Ball is a mass of incandescent gases. Right, no. A forgotten woman in science. Thank you. Oh, I can't wait to hear about that. Yeah, thank you guys. I would like to. Hopefully I will be just a little rest and it'll be all better. I don't like getting older. I think there's there are pros and cons to aging. Absolutely. So I'm glad I was able to be here tonight. Thank you. Thank you for joining me. I really appreciate you being here, and I hope you have a wonderful science week. Remember, stay curious. Yeah, stay lucky, right? Stay smart, stay healthy, stay better than me, right? Let's all try to do better than me. Yeah, stay lucky, everybody. I'll see you next week, maybe I'll see you on the interwebs in the meantime. Thank you. Good night.